So this is problem 14.7. It's on page 598. The subway train shown is traveling at a speed of 45 miles per hour when the brakes are fully applied on the wheels of cars A and B, causing them to slide on the track but are not applied on the wheels of car C. Knowing that the coefficient of kinetic friction is 30% between the wheels of the track, determine A, the time required to bring the train to a stop, and B, the force in each coupling. Okay. Try this to write properly. 14.7. So we've got three train cars. A, which is 30 ton. This way, the mass of A is 30 tons. And I'm going to switch color because I'm afraid the red may not show up well on the video. It's connected also to car B, as well as car, let's stick this one, C. Each one of these, let's see, mass of B. I'll just put the mass here and put the mass beneath each one. 40 tons. And C, 30 tons. Now we know that the initial speed V is 45 miles per hour. That's given in the figure. So the first thing let's do is convert that, that speed to feet per second. Let's see where we need to. Well, why don't we'll leave it as it is for now. We may want to convert it later, but time required to bring the train to the stop, if we leave it as it is, we'll get time in hours, which we could then convert to seconds, and that would be fine. But we're supposed to find that first, and then the force of in each coupling. Now the kinetic friction, mu, is 0.3, so the brakes are going to be locked up, basically, and the cars are going to slide on the tracks. So if we were to try and figure out how much force is applied to each of these cars in friction, we'd take 30% of the mass of car A, 30% of the mass of car B, and that's the total amount of frictional force applied to it. So it's a pretty straightforward, simple problem. Okay, now I need to make sure I've got tons there as a note so I don't forget the units. Okay, so we may have to convert this later, but for right now we'll work with it as it is. So what we're going to use is the impulse momentum equation, because notice one of the things about chapter 14 is that we're interested in time. Okay, one of the questions is how long does it take for the cars to come to a stop? If the question is how much distance is required for the cars to come to a stop, then you would go to chapter 13, because force times distance is really the topic of chapter 13. Force integrated over time is the topic of chapter 14. So look at what you're given to decide which method you're going to use. Okay, so anyway, the equation, our governing equation, is mv1 plus integral f dt equals mv2. Now, you may initially think we can only apply this to one particle, but that's not really the case. We can apply this equation to all three particles at the same time. They're chained together, right? You wouldn't separate the wheel from the car, for example, even though they have a joint between them. So why separate the cars? There's no need. So they all will have the same velocity in the initial and the final state. In fact, we know that they will all go to a stop, so the final velocity and therefore final momentum are zero. So basically, all of this momentum has to be taken away by an impulsive force, the friction force. So we need the total friction. Now remember I suggested that we should probably have a summation in that equation, or in that term, because there could be multiple forces acting on the bodies to slow them down. Now the force that acts on A, the frictional force that acts on A, does it just slow down A? No, A is coupled to B and C, so that force acts to slow down A, B, and C, just like the frictional force from B acts to slow down A, B, and C as well. So let's go off to the side and calculate the force, the frictional force on B and frictional force on A. That's pretty easy. The frictional force on A is just 30% of the weight of A, which is 30 tons. Now, tons is really a measure of mass, but for the sake of what we're doing here, we know that a ton is 2,000 pounds, so we could easily convert to pounds force. So let me just throw in 30 tons and be somewhat sloppy with this. Everything will work out when we're done. So Anyway, 30% of 30 tons, well, that would be what? I'm having trouble thinking, I'm sorry. It'd be 10% is 3, so 9, right? 9 tons. Okay, so there's the frictional force acting on A. The frictional force acting on B would be 30% of the mass of B, or the weight of B, really. So, let's see, 30% of that would be 3/4 is 12 tons. Okay, now to make sure that everything works out all right, I'm going to go ahead and convert the force here into pounds force, and I'm going to convert the weights into pounds mass so that all of my units will work out properly. So, since I have to multiply force times time here, I want to make sure I get the result right. So I'm just going to do it the safe way and go to pounds force. So 2,000 pounds force per ton means basically multiply this by 2, you get 24 times 1,000 is 24,000. So 24,000 pounds force is the frictional force on B. Similarly, if we were to take 2,000 times 9, that'd be 18,000. And there's the force acting on A and B. Okay? So now we have this sum of forces, basically. The sum of forces is just the frictional force on A plus the frictional force on B. And that's a total of 18 plus 24,000. And so that would be, what, 42,000? I did the math right? That should be the force acting on A, B, and C all together. And that's the sum of the forces. Okay. Now, the question is, how long does it take? Now, notice that this force that I've calculated here is a constant. This will happen quite frequently in the problems you see in this class, at least. So the force can come out because it's a constant. So it comes out of the integral. So what we really have is mv1 plus sum of force delta t equals 0. Because if you integrate the force, or if you integrate the time from 1 to 2, from moving to not moving, you're just going to get the total amount of time it takes to stop the cars. Yes?
The reason we left out the friction on C.
There is a reason. The reason is because the problem stated that the brakes are not applied on C. Good question. That's why we left off the frictional force on C. Okay, so we want to find this time, so let's just go ahead and solve for it. So delta t, the amount of time required, would be the initial momentum divided by the forces applied to overcome that momentum. Right? All I did was rearrange the equation. All right, so now that we've got the sum of forces, let me move over here and erase this bit. And see what we've got. Why don't we just go ahead and convert from miles per hour to feet per second. So there's 5280 feet per mile. That takes care of miles. And there are 3,600 seconds for each hour. So we'll have feet per second. So plug that in your calculator if you would, please. Let me know the speed of this thing. How much?
66.
66, thanks. So 66 feet per second is our initial speed. Now we can work in units that should give us a good result. So let me pull this equation up here. Delta t then is m. So what mass are we talking about? Well, all of the momentum of all the mass has to be taken out, right? So now we have to include the mass of A, B, and C because it's those three masses that are being slowed. And they're being slowed by the frictional force from just A and B. Okay? So the mass here is going to be the total mass. So you might look at this as a summation as well, okay, because we have to add multiple bodies together. But they're all moving the same way, so this should work out fine. So basically what we need is the mass of A plus the mass of B plus the mass of C. So that's 30 plus 40 plus 30. Obviously they've made the math very easy. So this is 100 tons. And I know this is not really a correct conversion, but the, well, no, this will be a correct conversion because we've got tons, which is mass. So let's convert it to pounds mass. There are 2,000 pound mass per ton. Now I'm running out of board space, so I'll have to go ahead and put these together and just write down the total mass in pounds mass. So 100 times 2,000, basically just take the 2 zeros, move it over here. We need a 2 with 5 zeros, and that will be our mass. So 2 with 1, 2, 3, 4, 5, zeros. There's the total mass that has to be slowed down, okay? It's moving at 66 feet per second, so we have to divide that then by the sum of the forces, which is 42,000 pounds force. So we have pounds mass and pounds force. What do we have to do? Convert. Yep. So let's just put it in the denominator so it'll all fit on the video screen. So there's 32.2 pound mass feet per second squared per each 1 pound force. So pounds force go away, pound mass go away, the feet will go away, and we will be left with seconds. Does everybody see how we're left with seconds? Seconds are in the denominator of the denominator, so they end up in the numerator. And so our time will be in seconds. So plug this into your calculator, please. Let's find out how long it takes for the train cars to come to rest.
9.76.
Yeah. 9.76?
Yeah.
All right, thanks. So let me put that over here because we're going to use it in just a second. So delta T equals 9.76 seconds. So almost 10 seconds that it takes for this thing to come to rest. The next question is, what is the force? Let's see, how do they state it? Find the force in each of the couplings. Okay, well that's a slightly different problem. Notice that the forces that we analyzed were forces that were all external to a system that we took, which was cars A, B, and C. But if we want to find the forces between the cars, now we will have to take each car independently, because now, if our system does not include B and C anymore, then there will be force from B and C onto A. Does that make sense? So I'm going to assume the direction of that force is this way. Does that make sense? So that's the force from B onto A. Because I know that C doesn't have its brakes on, so I imagine A is providing some braking for C. Therefore, the force on A would be in this direction. Yet I know that A slows down in 9.76 seconds. So now we'll write the equation again. It's really just the same equation used over and over again. So let me erase it just to write it again, basically. But this time, I'm just talking about the mass of A. Okay, just the mass of car A, plus the forces that act on it. There's still a summation from state 1 to state 2, from moving to not moving over time, equals mass of A velocity in state 2. Obviously, the velocity in state 2 is still 0, even though we're just talking about car A. The sum of the forces will still end up being a constant, though we have not figured out what they are yet. So we're going to pull them out. And basically what we find then is that the sum of the forces, and I'm going quick because I've only got 5 minutes, the sum of the forces would simply be the mass. Well, I better not go too quick because we're going to have a negative sign. All right, so mass of A V1 plus sum of forces delta T equals 0. So sum of forces would be equal to negative mass A V1 over delta T. Now this negative sign is not terribly important. Basically what it's saying is that the sum of the forces acting on car A must sum to this direction. Okay? So let's take this direction as the positive direction. Okay, to the left is positive. Then we'll be a little bit more careful when we look at the sum of forces on car A. The force from B onto A is a positive force. Okay? The force from the ground, from the friction essentially onto A, is a negative force. Now I'm not going to write equals mass times acceleration, even though that's true. All I care about is all of the forces acting on A that actually provide a significant change in the momentum of A. Does that make sense? Okay. Now unfortunately I've erased my frictional force on A.
It's 18,000.
Was it 18,000? Thanks. And that was pounds force? Okay. Okay, that makes sense. All right. So anyway, the sum of the forces is not really what I'm looking for. What I want to find is the force from B onto A. So that's going to be equal to, let's see, negative mass A V1 over delta T, and then the frictional force will move to this side as a positive number, plus Fa. Okay? So basically what I've done is I've broken this up into its two parts, and basically plugging this in here and then moving the frictional force to the other side. Okay? So we should be able to do this quickly. The mass of A is 30 tons times 2,000 would be 60. Let's see, did I do that right? 30. Yeah, that's right. 60,000 pounds mass multiplied by the initial velocity, 66 feet per second, divided by delta t, where delta t is 9.76 seconds. I'm trying to go too fast here because I've forgotten my negative sign. Okay, plus Fa, but Fa is going to be 18,000 pounds force. Okay? Now, I can't just add these two together because a pound mass foot per second squared is not a pound force. So what I would like to do is convert this one to a pound force. I'll do that by multiplying 1 pound mass, or how about 32.2? Well, it doesn't matter. 32.2 feet per second squared per each 1 pound force. Okay, so it's getting a little messy here because I've got to add this later. Pound mass goes away, feet per second squared goes away, and we'll end up with pounds force. So plug this in your calculator. Plug in negative 60,000, don't forget that negative sign, times 66, divided by 9.76, divided again by 32.2, and add 18,000 to it. Let's see what we get.
5,399.45.
Okay, how about if we say 5,400? Close enough? Anyone second that? Okay. So there's the force acting from B onto A. Now, if I had assumed the wrong direction, I would get a negative sign here. But that was the correct direction. How would we figure out the force between B and C? I'm out of time, so I can't do it, but how would you do it? Same way. That's right. Probably the easiest way is to figure out how much force it takes from B onto C to get C to slow down in 9.76 seconds. That's one system you could take, but you could take A and B as the system if you prefer. Okay? The reason I would prefer to take C as the system is because I would have a single force acting on it. If I take B and C as the system, then I have two more forces plus the force from C onto the two to take into account. Okay, so I'll leave this as an exercise for you to finish up.